For tonight's journey, we explore one of humanity's most profound cultural obsessions, the ancient and enduring question that has whispered through every civilization that ever gazed upward at the night sky. Are there other worlds out there, circling distant suns? This question has inspired philosophers, poets, scientists, and dreamers across millennia, appearing in ancient Greek texts, medieval manuscripts, Renaissance treatises, and modern science fiction. It represents perhaps our deepest curiosity about our place in the cosmos. So settle in, let your breathing slow, and allow your mind to drift among the stars as we trace the entire story of exoplanets, from ancient speculation to cutting-edge discovery, from philosophical musing to confirmed worlds orbiting alien suns. This is a tale of patience, ingenuity, wonder, and the gradual unveiling of a universe far richer and stranger than our ancestors ever imagined. Long before telescopes existed, long before humanity understood what stars truly were, people looked up and wondered. The ancient Greek philosopher Epicurus, writing around 300 years before the Common Era, proposed that the universe must contain infinite worlds, some like our own and some quite different. His reasoning was elegant in its simplicity. If atoms are infinite in number, he argued, and they combine in countless ways, then surely the combinations that produced our Earth must have occurred elsewhere, perhaps countless times, scattered throughout the boundless void. Democritus, another Greek thinker, had similar intuitions. He imagined a cosmos populated by innumerable worlds, some flourishing with life, others barren and desolate, all arising from the eternal dance of atoms through infinite space. These were not scientific theories in the modern sense, but rather philosophical frameworks for understanding existence. Yet they planted seeds that would eventually bloom into genuine scientific inquiry. For centuries, however, such ideas remained dangerous. The medieval worldview placed Earth firmly at the centre of creation, with the heavens arranged in crystalline spheres around our privileged position. To suggest other worlds existed was to challenge the cosmic order, to diminish humanity's special relationship with the divine. The Italian philosopher Giordano Bruno learned this lesson in the harshest possible way. In the late 1500s, he championed the idea of an infinite universe containing countless inhabited worlds. For this and other heresies, he was burned at the stake in Rome in the year 1600. His execution stands as a sombre reminder of how threatening the concept of other worlds once seemed to established powers, yet the idea would not die. When Nicholas Copernicus proposed that Earth orbited the Sun rather than vice versa, he inadvertently opened a door that could never be closed. If Earth was simply another planet circling the Sun, then perhaps the Sun was simply another star among many. And if that were true, then those countless points of light scattered across the night sky might each harbour their own families of worlds. The implications were staggering, humbling, and ultimately liberating. Galileo Galilei turned his primitive telescope toward the heavens in 1609 and 1610, revealing moons orbiting Jupiter, phases of Venus, and countless stars invisible to the naked eye. Each discovery chipped away at the old certainties. Johannes Kepler, working out the mathematical laws of planetary motion, dreamed of voyages to the moon and speculated about inhabitants on other worlds. The scientific revolution was underway, and with it came an ever-growing suspicion that our solar system might not be unique. By the 18th and 19th centuries, the plurality of worlds had become a respectable topic for scientific discussion. William Herschel, the great astronomer who discovered Uranus, believed that even the Sun might be inhabited, its dark sunspots representing glimpses of a cooler surface beneath the blazing exterior. While this particular idea proved incorrect, Herschel's broader intuition that the universe teemed with possibilities for life and habitation, aligned with the growing scientific consensus. The philosopher Immanuel Kant proposed that the fuzzy patches of light called nebulae might be distant island universes, vast collections of stars far beyond our own Milky Way. Each such galaxy, he reasoned, might contain countless solar systems, each potentially hosting planets of their own. The scale of the cosmos was expanding in human imagination, and with it the potential number of worlds. Yet for all this speculation, proof remained elusive. The stars were simply too far away, their light too faint, their hypothetical planets too small and dim to detect with existing technology. Astronomers could measure stellar positions, catalogue stellar brightnesses, and even begin to understand stellar compositions through the new science of spectroscopy. But planets around other stars remained firmly in the realm of theory and hope. The 19th century saw several claimed detections of exoplanets, but none withstood scrutiny. The challenges were simply too great. A planet like Jupiter, the largest in our solar system, would appear billions of times fainter than its parent star when viewed from interstellar distances. Trying to spot such a world would be like trying to see a firefly hovering next to a searchlight from thousands of miles away. The glare of the star would overwhelm any feeble planetary light. Some astronomers attempted to detect planets indirectly, by measuring the tiny wobbles they might induce in their parent stars. But the precision required exceeded what 19th and early 20th century instruments could achieve. The wobble induced by Jupiter on our Sun amounts to a velocity change of about 12 meters per second, roughly the speed of a brisk jog. Detecting such a subtle motion in the light of a star many light years away required technology that simply did not exist. And so the question lingered, tantalizing and unanswered. Were there planets orbiting other stars? Logic and probability suggested yes, but science demands evidence, and evidence remained frustratingly out of reach. Generations of astronomers lived and died without knowing the answer, passing the question on to their successors, like an inheritance of wonder. The 20th century brought tremendous advances in telescope technology, spectroscopy, and our understanding of stellar physics. Astronomers learned to read the life stories of stars in their spectra, to measure their temperatures, compositions, masses, and ages. They mapped the structure of our galaxy and discovered that it was but one among billions of galaxies scattered throughout an expanding universe. The cosmos revealed itself to be vaster and more ancient than anyone had imagined. Yet still, exoplanets eluded detection. Several announcements were made and later retracted. The instruments were not quite sensitive enough, the analysis techniques not quite refined enough, the systematic errors not quite understood well enough. Each false alarm taught valuable lessons, pushing the field toward greater rigor and better methods. But the confirmed discovery of a world beyond our solar system remained the great unclaimed prize of astronomy. By the 1980s, a new generation of instruments was coming online, spectrographs capable of measuring stellar velocities with unprecedented precision. The radial velocity method, which detects the gravitational tug of an orbiting planet on its star, was finally becoming feasible. Astronomers began systematic surveys, patiently monitoring nearby stars for the telltale wobbles that would betray hidden companions. The stage was set for discovery. Centuries of wondering, decades of technological development, and years of patient observation were about to pay off. The ancient question, posed by Epicurus and Democritus, championed by Bruno at the cost of his life, and pondered by countless stargazers throughout history, was finally about to receive a definitive answer. Other worlds existed, and humanity was on the verge of finding them. Let your mind drift now through those long centuries of waiting, through the patience of astronomers who knew they might never see the answer, through the gradual accumulation of knowledge that made discovery possible. The story of exoplanets is not just a story of distant worlds. It is a story of human curiosity, perseverance, and the slow but inexorable advance of understanding. And as you settle deeper into relaxation, know that the most exciting chapters of this story are still to come. The search for exoplanets was never simply a matter of pointing a telescope at a star and looking for planets. The fundamental challenge was one of contrast and scale, a problem so severe that it kept other worlds hidden from us for centuries, despite our burning desire to find them. Understanding this challenge helps us appreciate just how remarkable the eventual discoveries would be, and how ingenious the solutions that astronomers devised. Consider the basic problem of brightness. Our Sun, viewed from the distance of the nearest star system, Alpha Centauri, would appear as a moderately bright star, easily visible to the naked eye. But Earth, that pale blue dot we call home, would be roughly 10 billion times fainter than the Sun at visible wavelengths. 10 billion is a number so large that it defies easy comprehension. Imagine trying to spot a single candle flame positioned right next to a blazing lighthouse, viewed from 100 miles away, and you begin to grasp the difficulty. Jupiter, being larger and more reflective than Earth, would fare somewhat better, appearing perhaps 1 billion times fainter than the Sun rather than 10 billion. But 1 billion to 1 contrast ratio is still extraordinarily challenging. The glare of the star creates a sea of scattered light that drowns out any feeble planetary glow. Early telescopes had no hope of separating such disparate brightnesses. Even modern telescopes struggle with this task, requiring specialized instruments called coronagraphs to block the stellar light and reveal what might lurk nearby. The problem of distance compounds the difficulty. The nearest stars lie several light years away, meaning their light takes years to reach us. At such distances, even the largest planets would appear impossibly close to their parent stars from our perspective, separated by fractions of an arc-second, a unit of angular measurement so small that it corresponds to the apparent size of a coin viewed from several miles away. Distinguishing a planet from its star at such tight separations requires either extraordinary angular resolution or indirect detection methods that do not rely on seeing the planet directly. Scale presents another obstacle. Stars are huge compared to planets. Our Sun contains more than 99% of all the mass in the solar system. Jupiter, despite being the largest planet, contains only about 1/1000th of the Sun's mass. Earth is smaller still, massing only about 3/millionths of the Sun. When a planet orbits a star, both objects actually orbit their common centre of mass. But this centre lies so close to the star's centre that the star's motion is tiny. Detecting this subtle stellar wobble requires measuring velocities or positions with extraordinary precision. For the radial velocity method, which would eventually yield the first confirmed exoplanet around a Sun-like star, the required precision is measured in meters per second. Jupiter causes our Sun to wobble at about 12 meters per second, roughly the speed of a running human. Earth's influence is far smaller, causing a wobble of only about 9 centimeters per second, slower than a crawling infant. Measuring such tiny velocity shifts in the light of a star many light years away seemed like an impossible dream for much of astronomical history. Early attempts at exoplanet detection were plagued by systematic errors and instrumental limitations. In 1963, Peter van der Kamp announced that he had detected a planet orbiting Barnard's star, a red dwarf only 6 light years away. He based his claim on apparent wobbles in the star's position across the sky, detected through careful analysis of photographic plates accumulated over decades. The astronomical community was excited but cautious, and further investigation revealed that the wobbles were artifacts caused by adjustments to the telescope's optics. The claimed planet did not exist. Similar false alarms occurred throughout the 20th century. Each taught valuable lessons about the importance of understanding instrumental effects, the need for independent confirmation, and the dangers of seeing patterns in noisy data. The exoplanet community learned to be rigorous, demanding multiple lines of evidence before accepting any claimed detection. This culture of skepticism would serve the field well when genuine discoveries finally arrived. The atmosphere of Earth itself poses challenges for ground-based observations. Turbulence in the air causes stars to twinkle, blurring their images and introducing noise into precise measurements. Astronomers developed techniques to compensate for this atmospheric interference, including adaptive optics systems that deform telescope mirrors in real time to counteract the turbulence. But even with such corrections, the atmosphere limits what ground-based telescopes can achieve. Space-based telescopes avoid atmospheric problems entirely, observing from above the blanket of air that surrounds our planet. But launching telescopes into space is expensive and technically demanding. The instruments must be designed to survive the violence of launch, operate in the harsh environment of space, and return their data across millions of miles. Early space telescopes focused on other scientific goals, and dedicated exoplanet missions would not arrive until the 21st century. Temperature variations within telescopes and their instruments can mimic the signals of planets, causing apparent shifts in stellar spectra that have nothing to do with actual motion. Astronomers learned to control temperatures with exquisite precision, stabilizing their spectrographs to fractions of a degree. They developed calibration techniques using laser frequency combs and iodine absorption cells, providing reference standards against which stellar motions could be measured. The stars themselves are not perfectly quiet. Many stars pulsate, rotate, or experience surface activity that can masquerade as planetary signals. Sunspots on our own sun cause apparent velocity shifts of several meters per second as they rotate across the solar disk. Stellar flares, convective motions, and acoustic oscillations all contribute noise that must be understood and accounted for. Distinguishing genuine planetary signals from stellar noise requires careful analysis and often years of observations to build up confidence. Despite all these challenges, astronomers persevered. They refined their instruments, improved their analysis techniques, and accumulated ever longer baselines of observations. By the late 1980s and early 1990s, the precision of radial velocity measurements had improved to the point where detecting Jupiter-mass planets became feasible. The technology had finally caught up with the ambition. Simultaneously, other detection methods were being developed. The transit method, which looks for the tiny dimming of a star when a planet passes in front of it, offered a complementary approach. A Jupiter-sized planet transiting a Sun-like star would block about 1% of the star's light, a signal easily detectable with precise photometry. An Earth-sized planet would block only about 1/100th of 1%, far more challenging but not impossible with space-based instruments. The transit method has its own limitations. It only works when the planet's orbit happens to be aligned so that it crosses our line of sight to the star. For a planet in an Earth-like orbit around a Sun-like star, the probability of such an alignment is less than 1%. This means that transit surveys must monitor many thousands of stars to find a handful of transiting planets. But the method offers something that radial velocities alone cannot provide, a direct measurement of the planet's size, determined from how much light it blocks. Other methods were also being explored. Direct imaging aims to actually photograph planets by blocking the light of their parent stars, a technically demanding approach that works best for young, massive planets in wide orbits which are self-luminous and easier to separate from their stars. Gravitational microlensing uses the bending of light by gravity to detect planets around stars that happen to pass in front of more distant background stars. Astrometry measures the tiny positional wobbles of stars caused by orbiting planets, similar in principle to radial velocity, but measuring motion across the sky, rather than toward or away from us. Each method has its strengths and weaknesses, its biases towards certain types of planets and orbital configurations. Together, they provide complementary views of the exoplanet population, allowing astronomers to build a more complete picture than any single method could provide. The diversity of approaches reflects the ingenuity of the scientific community in tackling one of nature's most challenging puzzles. As the 20th century drew to a close, the pieces were finally in place. Decades of technological development had produced instruments capable of detecting the subtle signatures of distant worlds. Astronomers had learned from past false alarms and developed rigorous standards for confirming discoveries. The ancient question was about to be answered, not through philosophical argument or hopeful speculation, but through careful measurement and hard-won evidence. The first confirmed exoplanets were just around the corner, waiting to transform our understanding of the cosmos. Rest now in the knowledge that human ingenuity eventually overcomes even the most daunting challenges. The same patience and persistence that kept astronomers searching through centuries of failure would soon be rewarded beyond their wildest dreams. The universe was about to reveal its secrets, and the story of exoplanets was about to enter its most exciting chapter. The first confirmed discovery of planets beyond our solar system came from an unexpected direction, not from observations of ordinary sun-like stars, but from the precise timing of pulses from a dead stellar remnant. The year was 1992, and the discoverer was Alexander Fulcjan, a Polish astronomer working at the Arecibo Radio Telescope in Puerto Rico. His finding would mark the beginning of a new era in astronomy, though the strange nature of the planets he found meant that the full celebration would have to wait a few more years. Pulsars are the collapsed cores of massive stars that have exploded as supernovae. They're extraordinarily dense, packing more mass than our Sun into a sphere only about 20 kilometers across. As they spin, they emit beams of radio waves from their magnetic poles, like cosmic lighthouses sweeping their beams across the universe. When these beams happen to point toward Earth, we detect regular pulses of radio emission, ticking with remarkable precision. Fulcjan was studying a pulsar designated PSR B157+12, located about 2,300 light-years away in the constellation Virgo. He noticed that the pulses were not arriving with perfect regularity. Instead, they showed subtle variations, arriving sometimes slightly early and sometimes slightly late. The pattern of these variations suggested that the pulsar was being tugged back and forth by the gravitational influence of orbiting bodies. Analysis revealed at least 2 planets, later confirmed to be 3, orbiting this stellar corpse. The planets had masses comparable to Earth, making them the first Earth-mass planets ever detected outside our solar system. But their existence raised profound questions. How could planets survive the supernova explosion that created the pulsar? Were they formed from the debris of the explosion, coalescing from a disk of material around the newborn neutron star? Or were they captured from elsewhere? The pulsar planet discovery was groundbreaking, but it also felt somewhat alien and inaccessible. These were not worlds orbiting a warm, life-giving star like our Sun. They circled a dead stellar remnant, bathed in deadly radiation, utterly hostile to life as we know it. The discovery proved that planet formation was possible in the most extreme environments, but it did not answer the deeper question that most people cared about. Were there planets like Earth, orbiting stars like the Sun, where conditions, might allow for liquid water and perhaps even life. That question would be answered 3 years later, in 1995, when Michel Mayor and Didier Queloz announced a discovery that would shake the astronomical world to its foundations. Working at the Haute-Provence Observatory in southern France, they had detected a planet orbiting the star 51 Pegasi, a sun-like star located about 50 light-years away in the constellation Pegasus. The planet, designated 51 Pegasi b, was detected using the radial velocity method. Mayor and Queloz measured the subtle wobble of the star caused by the gravitational tug of its orbiting companion. The signal was unmistakable, a periodic variation in the star's velocity with an amplitude of about 59 meters per second. But the orbital period was shockingly short, just 4.2 days. This short period implied that the planet was extraordinarily close to its star, orbiting at only about 1/20th the distance between Earth and the Sun. At such close range, the planet would be intensely heated, its surface temperature reaching over 1,000 degrees Celsius. And the mass of the planet, inferred from the amplitude of the stellar wobble, was at least half the mass of Jupiter. Here was a giant planet, comparable in size to the largest world in our solar system, but orbiting so close to its star that it would complete a full year in less than a week. Nothing like this existed in our solar system. Jupiter orbits the Sun at a distance of about 5 astronomical units, taking nearly 12 years to complete one orbit. The idea of a Jupiter-mass planet in a 4-day orbit seemed almost absurd. Some astronomers initially suspected that the signal might be caused by stellar pulsations or some other form of stellar activity rather than a genuine planet. But the evidence held up under scrutiny. Independent teams confirmed the detection using different instruments and analysis techniques. The planet was real, and it forced astronomers to completely rethink their models of planet formation and evolution. The term hot Jupiter was coined to describe this new class of worlds, giant planets in scorchingly close orbits around their parent stars. How could such planets exist? The leading explanation involves planetary migration. Giant planets likely form in the cold outer regions of protoplanetary disks, where ices can condense and provide abundant material for building massive cores. But interactions with the disk, or with other planets, can cause these giants to spiral inward, migrating from their birthplaces to much closer orbits. If the migration is halted by some mechanism, perhaps the inner edge of the disk or tidal interactions with the star, the planet can end up in a stable close-in orbit. The discovery of 51 Pegasi b opened the floodgates. Within months, other teams announced additional hot Jupiter discoveries. The radial velocity surveys that had been patiently monitoring nearby stars for years suddenly began yielding planets at a remarkable rate. Each new discovery added to the growing catalogue and revealed the diversity of planetary systems in our galaxy. Upsilon Andromedae was found to host not one, but 3 giant planets, the first known multi-planet system around a sun-like star. The planets had orbits ranging from close in to more distant, hinting at complex dynamical histories. Some systems showed planets in highly elliptical orbits, stretched into elongated ovals, quite unlike the nearly circular paths of planets in our solar system. Others revealed planets in resonant configurations, their orbital periods related by simple ratios, suggesting past migration and gravitational interactions. The year 1999 brought the first detection of a transiting exoplanet. HD 29458b, another hot Jupiter, was observed to pass in front of its star, causing a slight dimming of the starlight. This transit detection confirmed the planetary nature of the companion and allowed astronomers to measure its size directly. The planet turned out to be larger than Jupiter, inflated by the intense heat from its nearby star. Transit observations also revealed that the planet had an atmosphere, with sodium detected in the starlight filtering through the planetary air during transit. By the early 2000s, the exoplanet count was growing steadily. Each year brought new discoveries, new surprises, and new questions. Giant planets were found at a range of orbital distances, from scorching close-in orbits to more temperate regions. Some stars hosted multiple planets, while others appeared to have solitary companions. The diversity was remarkable, and it became clear that our solar system, with its orderly arrangement of small rocky planets close in and giant planets farther out, was just one possible outcome among many. The Nobel Prize in Physics for 2019 was awarded to Michel Mayor and Didier Queloz for their discovery of 51 Pegasi b, recognizing the transformative impact of their work. The prize citation noted that their discovery started a revolution in astronomy, and that over 4,000 exoplanets had been found in the Milky Way since then. The ancient question of whether other worlds existed had been definitively answered, and a new field of science had been born. Alexander Fulstein's pulsar planets, while less celebrated in popular culture, remain a remarkable achievement. They demonstrated that planet formation is a robust process, capable of occurring even in the most extreme environments. The pulsar planets also showcase the power of precision timing as a detection method, a technique that continues to contribute to exoplanet science today. The early discoveries set the stage for everything that followed. They proved that exoplanets were abundant, that they came in unexpected varieties, and that our solar system was not necessarily typical. They motivated the development of new instruments and space missions dedicated to finding ever more planets. And they captured the public imagination, transforming the search for other worlds from a niche scientific pursuit into a topic of broad cultural interest. As you drift deeper into relaxation, consider the excitement of those early days, the thrill of confirming for the first time that other worlds truly existed. Imagine the late nights at telescopes, the careful analysis of data, the moment when the signal emerged unmistakably from the noise. These discoveries were the fruit of decades of preparation and centuries of wondering. They answered an ancient question and opened countless new ones. The story of exoplanets had begun in earnest, and the best was yet to come. The radial velocity method, which revealed 51 Pegasi b and launched the exoplanet revolution, remains one of the most powerful tools in the planet hunter's arsenal. Understanding how it works reveals the remarkable precision that astronomers have achieved and the ingenuity required to extract faint planetary signals from starlight. At its heart, the radial velocity method relies on a simple physical principle. When two objects orbit each other, they both move around their common centre of mass. A star with an orbiting planet is not stationary. Instead, it executes a small orbit of its own, a gentle wobble induced by the gravitational pull of its planetary companion. If we can detect this wobble, we can infer the presence of the planet, even though we never see the planet directly. The wobble reveals itself through the Doppler effect, the same phenomenon that causes the pitch of a siren to change as an ambulance passes by. When a star moves toward us, its light is shifted slightly toward shorter, bluer wavelengths. When it moves away, the light shifts toward longer, redder wavelengths. By measuring these tiny shifts in the wavelengths of spectral lines, astronomers can determine the star's velocity along our line of sight, its radial velocity. The spectral lines themselves are like cosmic fingerprints, patterns of absorption or emission at specific wavelengths caused by atoms and molecules in the star's atmosphere. Each element produces a characteristic set of lines, and these patterns are well known from laboratory measurements. By comparing the observed wavelengths of these lines to their known rest wavelengths, astronomers can calculate how fast the star is moving toward or away from us. The precision required is extraordinary. The wobble induced by a Jupiter-mass planet in a Jupiter-like orbit is only about 12 meters per second. For an Earth-mass planet in an Earth-like orbit, the wobble shrinks to a mere 9 centimeters per second, slower than a casual stroll. Detecting such tiny velocities requires measuring wavelength shifts of less than 1 part in a billion, a feat that pushes the limits of what is technically possible. Modern spectrographs achieve this precision through a combination of careful design and sophisticated calibration. The light from the star is spread into its component wavelengths by a diffraction grating or prism, creating a spectrum that is recorded by sensitive detectors. To measure wavelength shifts accurately, the instrument must be extraordinarily stable, immune to temperature changes, mechanical vibrations, and other sources of drift. One approach to calibration uses an iodine absorption cell, a container of iodine gas placed in the light path before the spectrograph. The iodine imprints a dense forest of absorption lines onto the stellar spectrum, providing a reference against which the stellar lines can be measured. Since the iodine lines have known wavelengths, any apparent shifts in the stellar lines can be corrected for instrumental effects. A more recent innovation is the laser frequency comb, a device that produces a spectrum of evenly spaced, ultra-stable laser lines. This comb of frequencies serves as an ideal wavelength reference, allowing calibration at the level of centimeters per second. Laser frequency combs have enabled the most precise radial velocity measurements ever made and are essential for detecting the tiny signals of Earth-mass planets. The HARPS spectrograph, installed on the European Southern Observatory's 3.6-meter telescope in Chile, has been one of the most successful radial velocity instruments. HARPS, which stands for High Accuracy Radial Velocity Planet Searcher, achieved a precision of about 1 meter per second, enabling the detection of planets only a few times more massive than Earth. Its successor, ESPRESSO, pushes precision even further, aiming for 10 centimeters per second and the ability to detect truly Earth-like planets around nearby stars. The radial velocity method has certain biases and limitations that shape the population of planets it can detect. Because the method measures motion along our line of sight, it is most sensitive to planets whose orbits are viewed edge-on. A planet in a face-on orbit, with its orbital plane perpendicular to our line of sight, produces no radial velocity signal at all, since the star moves side to side, rather than toward and away from us. For randomly oriented orbits, the method typically measures a lower limit on the planet's mass, since we do not know the orbital inclination. The method is also most sensitive to massive planets in close orbits. A more massive planet produces a larger stellar wobble, making it easier to detect. A closer orbit means a shorter orbital period, allowing the full wobble pattern to be observed more quickly. Hot Jupiters, with their high masses and short periods, are ideal targets for radial velocity detection, which is why they dominated the early discoveries. Detecting smaller planets, and those in longer period orbits, requires more patience and higher precision. An Earth-like planet in an Earth-like orbit would take a full year to complete one cycle of the radial velocity signal, and the signal itself would be barely detectable even with the best current instruments. Finding such a planet requires years of observations and careful removal of stellar noise. Stellar activity poses a significant challenge. Star spots, analogous to sunspots on our Sun, are cooler regions on the stellar surface that rotates with the star. As a star spot moves across the visible disk, it can mimic the signal of an orbiting planet, causing apparent velocity shifts that have nothing to do with actual motion. Magnetic activity cycles, stellar pulsations, and convective motions in the stellar atmosphere all contribute additional noise that must be understood and modelled. astronomers have developed sophisticated techniques to distinguish genuine planetary signals from stellar noise. They analyze the shapes of spectral lines, which can be distorted by star spots, and monitor indicators of stellar activity such as emission in certain spectral lines. They observe stars at multiple wavelengths, since stellar activity signals often vary with wavelength, while planetary signals do not. And they use statistical methods to assess the probability that an observed signal is caused by a planet rather than noise. Despite these challenges, the radial velocity method has been enormously successful. It has detected hundreds of exoplanets, including many of the first discoveries and numerous multi-planet systems. It remains the primary method for measuring planetary masses, since the transit method, while excellent for measuring sizes, does not directly reveal mass. Combining radial velocity and transit observations allows astronomers to determine both the mass and size of a planet, yielding its density and providing clues about its composition. The human stories behind radial velocity discoveries are as compelling as the science itself. Teams of astronomers have spent decades monitoring the same stars, accumulating observations night after night, year after year. They have weathered equipment failures, funding challenges, and the pressure of competition from rival groups. The discoveries they have made represent the culmination of tremendous dedication and perseverance. Consider the patience required to detect a planet like Jupiter, which takes 12 years to orbit the Sun. To confirm such a planet using radial velocities, astronomers must observe for at least one full orbital period, ideally more, to be confident that the signal is real and not an artifact. Detecting planets in even longer orbits requires even longer observational baselines. Some ongoing surveys have been running for more than 20 years, slowly building up the sensitivity to detect planets in the outer reaches of their systems. The radial velocity method also enables the study of planetary system architectures. By monitoring stars over long periods, astronomers can detect multiple planets in the same system, each contributing its own wobble to the star's motion. Disentangling these signals reveals the orbital periods, masses, and eccentricities of each planet, painting a picture of how the system is organized. Some systems show planets in resonant configurations, their orbits locked in simple ratios, while others display more chaotic arrangements. As you relax and let your thoughts wander, appreciate the elegance of the radial velocity method. It transforms an invisible planet into a detectable signal through the simple physics of gravity and light. It requires instruments of extraordinary precision and years of patient observation, and it has revealed a universe of planets far more diverse and abundant than we ever imagined. The wobbles of distant stars have become a language through which the cosmos speaks to us, telling stories of worlds we may never visit but can nonetheless come to know. The transit method offers a different window into the world of exoplanets, one that complements the radial velocity technique and has enabled some of the most spectacular discoveries in the field. Where radial velocities detect the gravitational tug of a planet on its star, transits detect the shadow of a planet as it passes between its star and Earth. This simple geometric alignment reveals not only the presence of a planet, but also its size, and in some cases, the composition of its atmosphere. Imagine watching a distant star, its light steady and unwavering across the void of space. Now, imagine that a planet orbits this star, and that the planet's orbital plane happens to be aligned so that it passes directly between the star and your vantage point. As the planet crosses the face of the star, it blocks a tiny fraction of the starlight, causing the star to appear slightly dimmer. This dimming is the transit signal, a periodic dip in brightness that repeats each time the planet completes an orbit. The depth of the transit dip reveals the size of the planet relative to its star. A larger planet blocks more light, producing a deeper dip. A Jupiter-sized planet transiting a Sun-like star blocks about 1% of the star's light, a signal easily detectable with precise photometry. An Earth-sized planet blocks only about 1/100th of 1%, a far more challenging signal, but still within reach of dedicated space telescopes. The duration of the transit depends on the planet's orbital speed and the size of the star. A planet in a close orbit moves quickly and crosses the stellar disk in a matter of hours. A planet in a more distant orbit moves more slowly and may take many hours or even a day to complete its transit. By measuring the transit duration along with the orbital period, astronomers can determine the planet's distance from its star and the geometry of its orbit. Transits also enable the study of planetary atmospheres through a technique called transmission spectroscopy. As the planet transits, some of the starlight passes through the thin ring of atmosphere at the planet's edge. Different molecules in the atmosphere absorb light at specific wavelengths, leaving characteristic fingerprints in the transmitted spectrum. By comparing the spectrum of the star during transit to its spectrum outside of transit, astronomers can identify the chemical constituents of the planetary atmosphere. This technique has revealed the presence of water vapor, carbon dioxide, methane, sodium, potassium, and other molecules in the atmospheres of various exoplanets. It has detected hazes and clouds that obscure the deeper atmosphere, and it has measured temperature profiles that reveal how heat is distributed around these alien worlds. Transmission spectroscopy is one of the most powerful tools for characterizing exoplanets, turning distant points of light into worlds with knowable properties. The transit method has a significant limitation. It only works when the planet's orbit is aligned so that it crosses our line of sight. For a planet in an Earth-like orbit around a Sun-like star, the probability of such an alignment is less than 1%. This means that for every transiting planet we detect, there are roughly 100 similar planets in non-transiting configurations that we miss entirely. Transit surveys must therefore monitor vast numbers of stars to find the lucky few with properly aligned planets. This requirement drove the design of dedicated transit hunting missions. The Kepler Space Telescope, launched in 2009, stared continuously at a single patch of sky containing about 150,000 stars, monitoring them for the telltale dips of transiting planets. The mission would revolutionize our understanding of exoplanets. But before we explore Kepler's extraordinary achievements, let us complete our understanding of the transit method itself. The geometry of transits provides information beyond just the planet's size. The shape of the transit light curve, the graph of brightness versus time, reveals details about the planet's orbit and even the star itself. As the planet begins to cross the stellar disk, the brightness drops gradually rather than instantaneously, because the planet first covers the limb of the star, where the light is slightly dimmer due to limb darkening. This effect occurs because we see deeper, hotter layers of the stellar atmosphere when looking at the centre of the disk compared to the cooler, higher layers visible at the edge. By modelling the precise shape of the transit light curve, astronomers can determine the inclination of the planet's orbit, its impact parameter describing how close to the centre of the stellar disk it passes, and even the density of the star itself. These parameters feed into our understanding of the entire system, constraining models of planet formation and evolution. Secondary eclipses occur when the planet passes behind the star, disappearing from view. During a secondary eclipse, the combined light of the star and planet drops slightly, as the planet's contribution is blocked. By measuring the depth of the secondary eclipse at different wavelengths, astronomers can determine the temperature of the planet's dayside and even map variations in brightness across its surface. Hot Jupiters with their intensely heated daysides produce detectable secondary eclipse signals that reveal how heat is transported from their permanent day sides to their eternal night sides. Phase curves track the brightness of the system as the planet orbits, revealing how the planet's apparent brightness changes as different portions of its surface rotate into view. A tidally locked hot Jupiter with one face perpetually turned toward its star shows maximum brightness just before secondary eclipse, when its hot day side is fully visible, and minimum brightness during transit when we see its cooler night side. Phase curves have revealed temperature maps of exoplanet surfaces, showing hot spots offset from the substellar point by atmospheric winds. The transit method also enables the detection of additional planets through transit timing variations. If multiple planets orbit the same star, their gravitational interactions cause slight changes in the timing of their transits. A planet might transit slightly early or late depending on where its companion is in its orbit. By analysing these timing variations, astronomers can detect non-transiting planets and measure the masses of transiting planets without needing radial velocity observations. Transit timing variations prove particularly powerful for systems discovered by Kepler, where the photometric precision was sufficient to detect timing shifts of just a few minutes. Several multi-planet systems had their architectures decoded through this technique, revealing planets that would otherwise have remained hidden. Ground-based transit surveys preceded the space missions and continue to contribute to valuable discoveries. Projects like SuperWasp in the Canary Islands and South Africa, HatNet spanning the globe, and KELT using small telephoto lenses have discovered hundreds of transiting planets, particularly hot Jupiters, whose deep transits are detectable from the ground. These surveys cover large areas of sky and can find planets around bright stars that are ideal for follow-up characterization. The transit method and radial velocity method complement each other beautifully. Transits reveal a planet's size but not its mass. Radial velocities reveal a planet's minimum mass but not its size. When both methods can be applied to the same planet, astronomers obtain both mass and radius, allowing them to calculate the planet's density. Density is a crucial clue to composition. A low-density planet must be composed largely of gas, like Jupiter or Saturn. A high-density planet is likely rocky, like Earth or Venus. Intermediate densities suggest water-rich compositions or thick atmospheres surrounding rocky cores. The combination of transit and radial velocity data has revealed the remarkable diversity of exoplanet compositions. Some planets are puffier than expected, inflated by unknown mechanisms that pump energy into their interiors. Others are denser than pure iron, challenging our understanding of planet formation. The data have revealed a population of super-Earths and mini-Neptunes with no analogue in our solar system. Worlds intermediate in size between Earth and Neptune that may be the most common type of planet in the galaxy. As you breathe slowly and let your body relax, consider the elegance of the transit method. A planet reveals itself not through direct observation, but through the shadow it casts, a fleeting dimming of starlight that repeats with clockwork regularity. This simple signal, properly interpreted, tells us the planet's size, its orbital period, its distance from its star, and even the composition of its atmosphere. From shadows we build worlds. The Kepler mission, Revolution in the Stars. The Kepler Space Telescope stands as one of the most transformative scientific instruments ever built. Launched on March 6, 2009, from Cape Canaveral in Florida, Kepler was designed with a singular purpose: to determine how common Earth-sized planets are in the habitable zones of Sun-like stars. Over its operational lifetime, it would exceed all expectations, discovering thousands of planets and fundamentally changing our understanding of planetary systems throughout the galaxy. The mission was named after Johannes Kepler, the 17th century German astronomer who discovered the laws of planetary motion. It was a fitting tribute, for the spacecraft that bore his name would reveal more about planets than Kepler himself could ever have imagined. The mission represented the culmination of decades of planning, technological development, and scientific advocacy, championed by principal investigator William Barucki, who had pursued the concept since the 1980s. Kepler's design was elegantly simple in concept, but extraordinarily demanding in execution. The spacecraft carried a photometer, an instrument designed to measure the brightness of stars with unprecedented precision. The photometer consisted of a 95-centimeter primary mirror that focused starlight onto a mosaic of 42 charge-coupled devices, the same type of light-sensitive chips used in digital cameras, but far more sensitive and carefully calibrated. The telescope stared continuously at a single patch of sky in the constellations Cygnus and Lyra, a region chosen because it contained a high density of stars and was positioned so that the spacecraft's solar panels could remain pointed at the sun while the telescope pointed at its target field. This fixed orientation allowed uninterrupted observations, essential for detecting the periodic dimming of transiting planets. Within this field of view, Kepler monitored approximately 150,000 stars simultaneously, recording their brightnesses every 30 minutes for most targets and every minute for a subset of particularly interesting stars. The data streamed back to Earth, where teams of scientists and sophisticated computer algorithms searched for the characteristic signatures of transiting planets. The precision required was extraordinary. To detect an Earth-sized planet transiting a Sun-like star, Kepler needed to measure brightness changes of about 84 parts per million, equivalent to detecting the dimming caused by a flea crawling across a car headlight, viewed from several miles away. Achieving this precision required not only an exquisitely sensitive instrument, but also careful correction for systematic effects, such as spacecraft pointing jitter, temperature variations, and the intrinsic variability of the stars themselves. Within months of beginning science operations, Kepler began finding planets. The first confirmed discoveries were hot Jupiters and other large planets in close orbits, the easiest targets to detect. But as data accumulated and analysis techniques improved, smaller and smaller planets emerged from the noise. By the end of its first year, Kepler had confirmed its first rocky planet, Kepler 10b, a world only about 1.5 times the diameter of Earth, but orbiting so close to its star that its surface was molten. The discoveries accelerated. Kepler 11, announced in February 2011, revealed a system of 6 planets orbiting a Sun-like star, all packed into orbits smaller than that of Venus. The planets ranged from about 2 to 4 times Earth's diameter, representing a class of world unknown in our solar system. The compact architecture of the system challenged models of planet formation and hinted at the diversity of planetary arrangements possible around other stars. Kepler 16b, announced later that year, was the first confirmed circumbinary planet, a world orbiting 2 stars rather than 1. Like Tatooine in the Star Wars films, this planet would experience double sunsets and a complex pattern of eclipses as its 2 suns orbited each other. The discovery proved that planets could form and survive in the gravitationally complex environment of binary star systems, expanding the range of potential planetary habitats. Kepler 22b, confirmed in December 2011, was the first planet found in the habitable zone of a Sun-like star. With a radius about 2.5 times that of Earth, it was likely too large to be rocky, but its discovery demonstrated that Kepler could find planets in the temperature range where liquid water might exist. The habitable zone, that Goldilocks region, neither too hot nor too cold, was no longer just a theoretical concept, but a place where real planets had been found. The discoveries kept coming, each one adding to our understanding of planetary diversity. Kepler 36 revealed 2 planets in adjacent orbits with dramatically different densities, one rocky and one puffy, raising questions about how such different worlds could form so close together. Kepler 62 presented a system with 5 planets, 2 of which orbited in the habitable zone and were small enough to potentially be rocky. Kepler 78b was found to be almost exactly the same size and mass as Earth, though it orbited so close to its star that its year lasted only 8.5 hours. In 2013, Kepler suffered a serious setback. The spacecraft used reaction wheels, spinning flywheels, that allowed it to maintain precise pointing without expending fuel. In May of that year, the second of 4 reaction wheels failed, leaving Kepler unable to point with sufficient stability to continue its original mission. The loss seemed devastating, potentially ending one of the most successful space missions in history. But ingenuity prevailed. Engineers devised a new mission concept called K2, which used the pressure of sunlight on the spacecraft's solar panels to help stabilize its pointing. By orienting the spacecraft so that sunlight pushed equally on both sides, and using the 2 remaining reaction wheels to control rotation, Kepler could achieve pointing stability sufficient for continued planet hunting, though in different regions of sky. The K2 mission observed a series of fields along the ecliptic plane, each for approximately 80 days before the spacecraft had to rotate to keep its solar panels illuminated. This new mode of operation opened up new scientific opportunities, allowing Kepler to observe different stellar populations and search for planets around nearby bright stars that were better suited for follow-up observations. K2 discovered hundreds of additional planets, including several notable systems. K2-18b, a planet about 8 times Earth's mass, orbiting in the habitable zone of a red dwarf star, would later become the target of atmospheric observations by the James Webb Space Telescope. K2 also observed the TRAPPIST-1 system, confirming additional planets and refining the orbital parameters of this remarkable collection of 7 Earth-sized worlds. Kepler's fuel finally ran out in October 2018, ending a mission that had lasted more than 9 years and transformed our understanding of the cosmos. The final tally was staggering: 2,662 confirmed planets, with thousands of additional candidates awaiting confirmation. Kepler had shown that planets were not rare exceptions but common companions to stars throughout the galaxy. Perhaps Kepler's most profound contribution was statistical. By surveying a large, well-characterized sample of stars and carefully accounting for the probability of detecting planets of various sizes and orbital periods, scientists could extrapolate from Kepler's discoveries to estimate the total population of planets in the galaxy. The results suggested that there are more planets than stars in the Milky Way, with billions of Earth-sized planets orbiting in the habitable zones of their stars. This statistical legacy continues to guide exoplanet science. We now know that small planets are far more common than large ones, that multi-planet systems are the norm rather than the exception, and that planetary systems come in a bewildering variety of configurations. Kepler revealed a universe rich with worlds, transforming the search for life beyond Earth from speculation into a tractable scientific program. The human stories behind Kepler are as inspiring as the science. William Barucki, who conceived the mission and championed it through decades of rejection before finally winning approval, lived to see his dream realized beyond all expectations. The thousands of scientists, engineers, and support staff who designed, built, launched, and operated the spacecraft contributed to one of humanity's greatest voyages of exploration. And the citizen scientists who participated in the Planet Hunters project, sifting through Kepler data to find planets that automated algorithms missed, demonstrated the power of public engagement in scientific discovery. As you rest and let your thoughts drift among the stars, consider Kepler's legacy. A single telescope, staring at a single patch of sky, revealed thousands of worlds and transformed our understanding of our place in the universe. The mission showed that planets are everywhere, that Earth-sized worlds are common, and that the galaxy teems with possibilities for life. Kepler's light may have faded, but its discoveries illuminate the path forward, guiding the next generation of planet hunters toward ever more remarkable findings. TESS and the new generation of planet hunters. Even as Kepler was revolutionizing exoplanet science, plans were underway for the next generation of transit hunting missions. The Transiting Exoplanet Survey satellite, known as TESS, launched on April 18, 2018, just months before Kepler's final shutdown. Where Kepler stared deeply at a single field, TESS was designed to survey nearly the entire sky, searching for planets around the nearest and brightest stars. The shift in strategy reflected the evolving goals of exoplanet science. Kepler's primary mission was statistical, determining how common various types of planets were throughout the galaxy. This required observing a large number of stars for an extended period, even if many of those stars were faint and distant. TESS, by contrast, was designed to find planets that could be studied in detail by follow-up observations, particularly atmospheric characterization with large ground-based telescopes and the James Webb Space Telescope. TESS carries 4 wide-field cameras, each monitoring a 24 by 24 degree patch of sky. The spacecraft divides the sky into overlapping sectors, observing each sector for about 27 days before moving on to the next. Over its 2-year primary mission, TESS observed most of the sky, with regions near the ecliptic poles receiving the longest continuous coverage due to the overlap of multiple sectors. The cameras are optimized for detecting transits around red dwarf stars, which are smaller and cooler than the Sun. When an Earth-sized planet transits a red dwarf, it blocks a larger fraction of the star's light than it would for a Sun-like star, making the transit easier to detect. Red dwarfs are also the most common type of star in the galaxy, and their habitable zones are closer in, meaning habitable zone planets have shorter orbital periods and transit more frequently. TESS's first confirmed planet, announced in September 2018, was Pi Mensae C, a super-Earth orbiting a nearby Sun-like star. The planet had been previously detected through radial velocity observations, but TESS revealed that it also transited, allowing its size to be measured. The combination of mass from radial velocities and radius from transits showed that Pi Mensae C was likely a dense, rocky world. The discoveries accumulated rapidly. LHS 3844b, a rocky planet slightly larger than Earth orbiting a red dwarf only 49 light-years away, was found to have no significant atmosphere, its surface exposed directly to the harsh radiation of its star. TOI 700d, announced in January 2020, was the first Earth-sized planet in the habitable zone discovered by TESS, orbiting a red dwarf about 100 light-years away. The system was later found to contain additional planets, including another potentially habitable world. TESS has proven particularly adept at finding planets in multi-planet systems. TOI 178, located about 200 light-years away, hosts at least 6 planets in a remarkable chain of resonances, their orbital periods related by simple ratios. Such resonant chains are thought to be signatures of gentle migration through the protoplanetary disk, preserving the delicate gravitational relationships that would be disrupted by more violent dynamical histories. The mission has also discovered planets around unusual stars. TOI 1338b is a circumbinary planet orbiting a pair of stars that eclipse each other every 15 days. The planet was discovered by a high school intern examining TESS data, demonstrating that significant discoveries can come from unexpected sources. TESS has found planets around stars in binary systems, around stars with unusual compositions, and around stars at various stages of their evolution. One of TESS's most important contributions is providing targets for atmospheric characterization. The James Webb Space Telescope, launched in December 2021, can study the atmospheres of transiting planets by observing how starlight filters through the planetary atmosphere during transit. But JWST's time is precious, and it can only observe a limited number of targets. TESS provides a curated list of the best candidates, planets around bright, nearby stars where atmospheric signals are strongest. TESS's extended mission, approved after the successful completion of its primary mission, continues to survey the sky with improved observing strategies. Some sectors are now observed for longer periods, increasing sensitivity to smaller planets and those in longer orbits. The mission is expected to continue operating for years to come, steadily adding to the catalogue of known exoplanets. The pipeline from TESS detection to confirmed planet involves multiple steps. When the automated algorithms identify a potential transit signal, it is designated a TESS object of interest, or TOI. These candidates then undergo vetting to rule out false positives, such as eclipsing binary stars, instrumental artifacts, or background objects. Promising candidates are followed up with ground-based observations, including radial velocity measurements to confirm the planetary nature and determine the mass. Community involvement has been crucial to TESS's success. The data are made publicly available, allowing astronomers around the world to search for planets and conduct follow-up observations. Citizen science projects engage the public in examining light curves, and professional-amateur collaborations have contributed to many discoveries. The open nature of the mission has accelerated the pace of discovery and broadened participation in exoplanet science. TESS has also made contributions beyond exoplanets. The continuous monitoring of millions of stars has revealed stellar variability, flares, and oscillations that inform our understanding of stellar physics. The mission has detected supernova, observed asteroids and comets, and even captured images of a comet passing through the solar system. The wide-field design that makes TESS effective for finding transiting planets also makes it a powerful tool for time-domain astronomy more broadly. As you settle deeper into relaxation, consider the complementary roles of Kepler and TESS. Kepler told us how common planets are, surveying a distant field to build up statistics on planetary occurrence. TESS tells us which planets we can study in detail, finding worlds around nearby bright stars that are amenable to follow-up characterization. Together, they have transformed exoplanet science from a discovery-driven field to one focused on understanding the nature and diversity of planetary systems. The torch continues to pass to new missions and new instruments. Ground-based surveys continue to find planets, radial velocity programs push toward ever greater precision, and future space missions promise even more remarkable discoveries. But TESS remains at the forefront, a tireless surveyor of the sky, revealing world after world around the stars nearest to our Sun. Other detection methods completing the toolkit. While the transit and radial velocity methods have discovered the majority of known exoplanets, other techniques contribute essential pieces to the puzzle. Each method has its own strengths and biases, sensitive to different types of planets in different orbital configurations. Together, they provide a more complete census of the planetary population than any single method could achieve. Direct imaging represents the most intuitive approach to finding exoplanets. Simply take a picture of them. In practice, this is extraordinarily difficult due to the overwhelming brightness of the parent star compared to any orbiting planet. The contrast ratio between a Sun-like star and an Earth-like planet at visible wavelengths is about 10 billion to 1, comparable to trying to photograph a firefly hovering next to a searchlight from miles away. Despite these challenges, direct imaging has succeeded in detecting a growing number of exoplanets. The key is to observe at infrared wavelengths, where the contrast ratio is more favourable, and to use coronagraphs or star shades that block the light of the star. Young planets are particularly good targets because they are still hot from their formation, glowing brightly in the infrared as they radiate away their primordial heat. The first directly imaged exoplanet was 2M I7b, discovered in 2004, orbiting a brown dwarf about 170 light-years away. The planet is several times the mass of Jupiter and orbits at a large distance from its host, making it relatively easy to separate from the dim brown dwarf. Since then, direct imaging has revealed several multi-planet systems, including HR 8799, which hosts at least 4 giant planets that have been individually photographed. Direct imaging provides information that other methods cannot. By capturing the light from the planet itself, astronomers can study its atmosphere directly, without relying on the filtering effect of transits. Spectroscopy of directly imaged planets has revealed the presence of water vapour, carbon monoxide, and methane in their atmospheres, along with clouds and hazes that affect their appearance. The technique is currently limited to young massive planets in wide orbits, the easiest targets to detect. Imaging an Earth-like planet around a Sun-like star remains beyond current capabilities, but future missions are being designed with this goal in mind. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will carry a coronagraph technology demonstrator that will push the boundaries of what is possible. The Habitable Worlds Observatory, a concept for a future flagship mission, aims to directly image Earth-like planets in the habitable zones of nearby stars. Gravitational microlensing offers a completely different approach to planet detection, one that exploits the bending of light by gravity predicted by Einstein's general theory of relativity. When a star passes almost directly in front of a more distant background star, its gravity acts as a lens, magnifying and brightening the background star's light. If the foreground star has a planet, the planet's gravity can produce an additional, brief spike in the magnification. Microlensing events are rare and unpredictable, requiring continuous monitoring of millions of stars to catch them. The signals are typically one-time events, since the precise alignment required is unlikely to recur. But microlensing has unique advantages. It is sensitive to planets at large orbital distances, in the region where our own Jupiter and Saturn reside, where other methods struggle. It can detect planets around stars too faint or too distant for radial velocity or transit observations. And it can find free-floating planets, worlds that drift through the galaxy unbound to any star. Surveys like OGLE, MOA, and KMTNet have detected more than 100 planets through microlensing, including some of the most distant exoplanets known. Statistical analyses of microlensing data suggest that free-floating planets may be remarkably common, potentially outnumbering stars in the galaxy. These orphan worlds, ejected from their birth systems through gravitational interactions, drift alone through the darkness, invisible except when they happen to pass in front of a background star. The Nancy Grace Roman Space Telescope will conduct a large-scale microlensing survey, monitoring hundreds of millions of stars toward the galactic centre. This survey is expected to discover thousands of exoplanets including many in the outer regions of their systems, and potentially hundreds of free-floating planets. The statistical sample will complement the discoveries from transit and radial velocity surveys, filling in our understanding of planetary populations at larger orbital distances. Astrometry measures the tiny positional wobbles of stars caused by orbiting planets, similar in principle to the radial velocity method, but detecting motion across the sky rather than toward or away from us. The technique requires extraordinarily precise measurements of stellar positions, tracking shifts of microarc seconds, angles so small that they correspond to the width of a human hair, seen from hundreds of miles away. Ground-based astrometry has struggled to achieve the precision needed for exoplanet detection, limited by atmospheric turbulence and instrumental effects. But the Gaia space mission, launched by the European Space Agency in 2013, is revolutionizing the field. Gaia is measuring the positions, distances, and motions of more than 1 billion stars with unprecedented accuracy, creating a 3-dimensional map of the Milky Way. As Gaia accumulates data over its multi-year mission, it is becoming sensitive to the astrometric wobbles induced by massive planets in long-period orbits. The mission has already confirmed several exoplanets through astrometry and is expected to detect thousands more as the data baseline extends. Astrometry is particularly powerful for determining the true masses of planets, since it measures the full 3-dimensional motion of the star rather than just the component along our line of sight. Timing methods detect planets through their gravitational influence on periodic signals from their host stars or other objects in the system. The first confirmed exoplanets, the pulsar planets, around PSR B27+12, were discovered through variations in the arrival times of radio pulses. Similar techniques have been applied to other types of periodic signals, including the pulsations of variable stars and the eclipses of binary star systems. Transit timing variations mentioned earlier use the slight changes in the timing of transits caused by gravitational interactions between planets in multi-planet systems. This technique has been particularly powerful for systems discovered by Kepler, where the photometric precision allows detection of timing shifts of just a few minutes. Transit timing variations can reveal non-transiting planets and measure the masses of transiting planets, providing a complete picture of system architecture. Each detection method illuminates a different portion of the exoplanet population. Radial velocities find massive planets in close orbits around nearby stars. Transits find planets of all sizes whose orbits happen to be aligned with our line of sight. Direct imaging finds young, massive planets in wide orbits. Microlensing finds planets at intermediate to large distances, including free-floating worlds. Astrometry finds massive planets in long-period orbits. Together, these methods reveal the full diversity of planetary systems, from scorching hot Jupiters to frozen super-Earths, from tightly packed systems to lonely worlds drifting through interstellar space. As you breathe slowly and let your mind wander, appreciate the ingenuity that has gone into developing these diverse techniques. Each method overcomes different challenges, exploits different physical principles, and reveals different aspects of the planetary population. The toolkit of exoplanet detection continues to expand, with new methods and new instruments constantly pushing the boundaries of what we can discover. The universe is generous with its secrets, rewarding our curiosity with an ever-growing catalogue of alien worlds. The diversity of exoplanets, a cosmic zoo. The thousands of exoplanets discovered over the past 3 decades have revealed a universe far stranger and more diverse than anyone anticipated. Our solar system, with its orderly arrangement of rocky planets close to the Sun and gas giants farther out, turns out to be just one possibility among countless variations. The exoplanet population includes worlds that would seem at home in science fiction, challenging our understanding of how planets form and evolve. Hot Jupiters remain among the most striking examples of planetary diversity. These gas giants, comparable in mass to Jupiter but orbiting their stars in just days rather than years, were the first exoplanets discovered around Sun-like stars and continue to puzzle scientists. Their existence was entirely unexpected, since the cold temperatures needed to form giant planet cores were thought to exist only in the outer regions of protoplanetary disks. The leading explanation for hot Jupiters involves migration. These planets likely formed beyond the snowline, where water ice could condense and provide abundant solid material for building massive cores. Interactions with the protoplanetary disk, or gravitational scattering by other planets, then caused them to spiral inward, eventually settling into close orbits. Some hot Jupiters may have arrived at their current positions through high eccentricity migration, where gravitational interactions with distant companions pumped up their orbital eccentricities until tidal interactions with the star circularized their orbits at small distances. Hot Jupiters display remarkable atmospheric properties. Their permanent day sides, forever facing their stars due to tidal locking, reach temperatures of thousands of degrees, hot enough to vaporize rock and iron. Their night sides, eternally dark, are much cooler, creating extreme temperature contrasts that drive powerful atmospheric circulation. Observations have revealed supersonic winds, exotic clouds of titanium oxide and vanadium oxide, and even iron rain on some of these extreme worlds. WASP 76b, a hot Jupiter about 640 light-years away, provides a vivid example. Observations with the espresso spectrograph detected iron vapor in the planet's atmosphere on the evening terminator, the boundary between day and night. On the cooler morning terminator, the iron signal was absent, suggesting that iron condenses into droplets on the night side and rains down, only to be vaporized again as atmospheric circulation carries it back to the day side. Iron rain falling on an alien world, a phenomenon that would have seemed fantastical just decades ago, is now a scientifically supported reality. At the opposite extreme from hot Jupiters lie the super-Earths and mini-Neptunes, planets with masses and radii intermediate between Earth and Neptune. These worlds have no analogue in our solar system, yet they appear to be among the most common types of planets in the galaxy. Kepler revealed that planets between 1 and 4 times Earth's radius orbit a substantial fraction of Sun-like stars, raising questions about their compositions and formation histories. The boundary between super-Earths and mini-Neptunes is not sharply defined, but observations suggest a transition around 1.5 to 2 Earth radii. Planets smaller than this threshold tend to have high densities, consistent with rocky compositions, while larger planets have lower densities that require significant amounts of gas or water. This radius valley may reflect the loss of primordial hydrogen atmospheres from smaller planets, stripped away by stellar radiation or outgassed from cooling interiors. Some super-Earths may be ocean worlds, planets with so much water that it comprises a significant fraction of their total mass. On such worlds, water could exist in exotic high-pressure phases, with liquid oceans overlying layers of ice compressed into forms unknown on Earth. The habitability of ocean worlds is uncertain, since the high-pressure ice layer might prevent contact between the ocean and a rocky seafloor, potentially limiting the chemical cycles that support life on Earth. Lava worlds represent another extreme. Planets like Coro T7b and Kepler 10b orbit so close to their stars that their surfaces are molten, covered in oceans of magma rather than water. These worlds may have atmospheres of vaporized rock, with clouds of silicon dioxide and rain of liquid minerals. The intense stellar radiation drives continuous evaporation from the day side, creating comet-like tails of escaping material that have been detected through careful observations. Rogue planets, also called free-floating planets, drift through the galaxy without orbiting any star. These worlds may have been ejected from their birth systems through gravitational interactions with other planets, or they may have formed independently in the collapse of small molecular cloud cores. Microlensing surveys suggest that rogue planets may be surprisingly common, potentially outnumbering stars in the Milky Way. Life on a rogue planet would face extreme challenges. Without a nearby star to provide warmth, the surface would be frozen solid, far colder than any place in our solar system. But internal heat from radioactive decay could potentially maintain liquid water beneath a thick ice shell, similar to the subsurface oceans suspected to exist on moons like Europa and Enceladus. A sufficiently massive rogue planet with a thick hydrogen atmosphere might even retain enough heat to keep surface water liquid, warmed by the pressure-induced greenhouse effect rather than starlight. Circumbinary planets orbit two stars rather than one, experiencing double sunrises and complex patterns of illumination. The first confirmed circumbinary planet, Kepler 16b, was announced in 2011, revealing that the Tatooine-like worlds of science fiction were scientific fact. Since then, more than a dozen circumbinary planets have been discovered, all giants in relatively wide orbits. The formation of circumbinary planets presents theoretical challenges. The gravitational influence of two stars creates a chaotic zone near the binary where stable orbits are impossible. Planets must either form farther out and migrate inward, stopping at the edge of the unstable zone, or form from material that has been shepherded into stable configurations by the binary's gravity. The existence of circumbinary planets demonstrates the resilience of planet formation, succeeding even in gravitationally complex environments. Eccentric planets follow elongated orbits that carry them much closer to their stars at some times than at others. HD 80606b, a giant planet about 190 light-years away, has one of the most extreme orbits known, with an eccentricity of about 0.93. At its closest approach, the planet skims just a few million miles from its star, receiving intense radiation that heats its atmosphere by hundreds of degrees in a matter of hours. At its farthest point, it retreats to a distance comparable to Earth's orbit, cooling dramatically before plunging back toward the stellar furnace. The diversity extends to planetary system architectures. Some systems are tightly packed, with multiple planets orbiting within the distance of Mercury's orbit around the Sun. Kepler 11, with 6 planets inside the orbit of Venus, exemplifies this compact configuration. Other systems are more spread out, with planets at a range of distances. Some show resonant chains, where orbital periods are related by simple ratios, while others display more chaotic arrangements that may have resulted from past instabilities. The Radius Valley, a deficit of planets between about 1.5 and 2 Earth radii, represents one of the most intriguing features of the exoplanet population. This gap separates the rocky super-Earths from the gas-rich mini-Neptunes and likely reflects the processes that shape planetary atmospheres. Smaller planets may lose their primordial hydrogen envelopes through photoevaporation, stripped away by stellar radiation, or through core-powered mass loss, driven by heat escaping from the planet's interior. Larger planets retain their atmospheres, remaining puffy and low density. As you rest and let your imagination wander, picture this cosmic zoo of worlds. Imagine standing on the molten surface of a lava planet, watching the sky glow red with the light of a nearby star. Imagine floating in the ocean of a water world with ice below and clouds above. no land in sight. Imagine the double shadows cast by twin suns on a circumbinary world, or the eternal darkness of a rogue planet drifting through the void. The universe has proven more creative than our most inventive storytellers, offering a diversity of worlds that challenges and delights in equal measure. The search for habitable worlds. Among all the questions that drive exoplanet science, none captures the imagination more powerfully than the search for habitable worlds. Could there be planets out there where conditions are right for life as we know it? Could alien organisms swim in extraterrestrial oceans, grow in alien soils, or gaze up at unfamiliar stars, and wonder, as we do, whether they are alone? The search for habitable exoplanets brings together astronomy, planetary science, chemistry, and biology in a quest that may ultimately answer one of humanity's oldest questions. The concept of the habitable zone provides a starting framework for this search, though reality proves far more nuanced than any simple definition can capture. The habitable zone, sometimes called the Goldilocks zone, refers to the range of distances from a star where a planet with the right atmospheric conditions could maintain liquid water on its surface. Not too hot, not too cold, but just right for the water that seems essential to life, as we understand it. The boundaries of the habitable zone depend on the luminosity of the star. A bright, hot star has a habitable zone that lies farther out, while a dim, cool star has a habitable zone much closer in. For our Sun, the habitable zone is often estimated to extend from about 0.95 to 1.7 astronomical units, with Earth sitting comfortably within this range and Mars hovering near the outer edge. Venus, despite being within some definitions of the habitable zone, demonstrates that location alone does not guarantee habitability, as its runaway greenhouse effect has created surface temperatures hot enough to melt lead. The inner edge of the habitable zone is set by the runaway greenhouse effect. As a planet moves closer to its star, it receives more radiation, which warms the surface and evaporates more water into the atmosphere. Water vapour is a potent greenhouse gas, trapping heat and warming the planet further. Beyond a certain threshold, this feedback becomes unstoppable, evaporating all surface water and creating a thick steam atmosphere that eventually escapes to space. Venus likely underwent this process early in its history, losing whatever oceans it may once have possessed. The outer edge of the habitable zone is set by the maximum greenhouse effect that carbon dioxide can provide. As a planet moves farther from its star, it receives less radiation and cools. Carbon dioxide released from volcanoes can accumulate in the atmosphere, trapping heat and warming the surface. But beyond a certain distance, even a thick carbon dioxide atmosphere cannot maintain temperatures above freezing. Carbon dioxide itself begins to condense into clouds and eventually snow, limiting the greenhouse warming it can provide. These boundaries are not sharp lines but fuzzy regions that depend on many factors beyond simple distance. The composition of the atmosphere, the presence of clouds, the reflectivity of the surface, the planet's rotation rate, and the distribution of land and water all influence whether a planet can maintain habitable conditions. A planet with a hydrogen-rich atmosphere could remain habitable much farther from its star than one with an Earth-like atmosphere. A planet with high reflectivity might remain cool even close to its star. The habitable zone concept also assumes that liquid water is necessary for life, a reasonable assumption given that all life on Earth requires water, but potentially limiting if life can arise through different chemistry. Some astrobiologists speculate about life based on other solvents, such as liquid methane on cold worlds, like Titan, or liquid ammonia on even colder bodies. If such alternative biochemistries exist, the range of potentially habitable environments would expand dramatically. Red dwarf stars, the most common type of star in the galaxy, present both opportunities and challenges for habitability. Their habitable zones lie close to the star, where planets are likely to be tidally locked, with one face perpetually turned toward the star and the other in eternal darkness. Early concerns suggested that tidally locked planets would be uninhabitable, with their day sides scorched and their night sides frozen, and their atmospheres potentially collapsing as gases froze out on the cold side. However, more sophisticated climate models have shown that atmospheric circulation can redistribute and heat effectively, preventing atmospheric collapse and maintaining temperate conditions over much of the planet. A thick atmosphere, or a global ocean, could further moderate temperatures, creating habitable conditions even on a tidally locked world. The permanent day side might be too hot and the permanent night side too cold, but a ring of twilight around the terminator could offer comfortable temperatures. Red dwarfs pose other challenges for habitability. They're prone to powerful flares, especially when young, that could strip away planetary atmospheres and bathe surfaces in harmful radiation. Their habitable zones lie so close that planets experience strong tidal forces, which might cause excessive volcanic activity or lock planetary rotation early in their histories. And red dwarfs take billions of years to settle onto the main sequence, during which time their luminosities decrease, potentially freezing planets that formed in the habitable zone. Despite these challenges, red dwarfs remain attractive targets for the search for habitable worlds. Their small size makes transiting planets easier to detect, since the planet blocks a larger fraction of the star's light. Their low luminosities mean that habitable zone planets have short orbital periods, making transit signals repeat frequently and accumulate quickly. And their sheer abundance means that even if only a small fraction host habitable planets, the total number could be enormous. The TRAPPIST-1 system stands as the most remarkable example of potentially habitable worlds around a red dwarf. Located about 40 light-years away in the constellation Aquarius, TRAPPIST-1 is an ultra-cool dwarf star with a mass only about 9% that of the Sun and a luminosity less than 0.1% of solar. Despite its diminutive size, this tiny star hosts 7 Earth-sized planets, all detected through their transits and confirmed through transit timing variations. The discovery of the TRAPPIST-1 system unfolded gradually, building anticipation with each new finding. The first 3 planets were announced in May 2016, discovered by the TRAPPIST Telescope in Chile, a small robotic instrument designed specifically to search for planets around ultra-cool dwarfs. Follow-up observations with larger telescopes, including the Spitzer Space Telescope, revealed 4 additional planets, bringing the total to 7 in February 2017. The 7 planets of TRAPPIST-1 are designated B through H in order of increasing distance from the star. All 7 have sizes similar to Earth, ranging from about 75% to 112% of Earth's diameter. Their orbital periods range from 1.5 days for the innermost planet to about 19 days for the outermost, all fitting comfortably inside the orbit of Mercury around our Sun. The system is extraordinarily compact, with all 7 planets orbiting closer to their star than Mercury orbits the Sun. 3 of the TRAPPIST-1 planets, designated E, F and G, orbit within the habitable zone, where liquid water could potentially exist on their surfaces. TRAPPIST-1e is particularly intriguing, with a size and density suggesting a rocky composition similar to Earth. Climate models suggest that, with the right atmospheric conditions, TRAPPIST-1ce could maintain temperate surface temperatures, making it one of the most promising targets in the search for habitable worlds. The planets of TRAPPIST-1 are locked in a remarkable chain of resonances. their orbital periods related by simple ratios. For every 8 orbits of the outermost planet H, the inner planets complete 2, 3, 4, 6, 9, 15, and 24 orbits respectively, creating a gravitational symphony that has persisted for billions of years. This resonant chain suggests that the planets migrated inward through the protoplanetary disk, becoming trapped in resonance as they approach their current positions. The resonant configuration allows precise measurement of the planet's masses through transit timing variations. As the planets tug on each other gravitationally, their transit times shift by minutes, revealing the strength of their mutual interactions. These measurements have yielded masses for all 7 planets, showing that most have densities consistent with rocky compositions, though some may have significant amounts of water or other volatiles. Proxima Centauri b holds the distinction of being the nearest known exoplanet, orbiting the closest star to our Sun at a distance of just 4.2 light-years. Proxima Centauri is a red dwarf, the smallest and dimmest member of the Alpha Centauri triple star system. The planet was discovered in 2016 through radial velocity observations, which detected the star's wobble induced by the planet's gravity. Proxima Centauri b has a minimum mass of about 1.3 Earth masses and orbits in the habitable zone of its star, completing one orbit every 11.2 days. Its proximity makes it an extraordinarily attractive target for study, though its non-transiting geometry limits what can be learned through current techniques. Future missions with advanced direct imaging capabilities might be able to photograph this nearby world, revealing details about its atmosphere and surface. The habitability of Proxima Centauri b remains uncertain. The planet receives about 65% of the radiation that Earth receives from the Sun, placing it within the habitable zone. But Proxima Centauri is an active flare star, prone to powerful outbursts that could erode any atmosphere. Whether the planet has retained an atmosphere and whether that atmosphere could support liquid water are questions that await future observations. In 2019, astronomers announced the discovery of a second planet in the Proxima Centauri system. Proxima Centauri c is a super-Earth or mini-Neptune with a mass of at least 7 Earth masses, orbiting at about 1.5 astronomical units with a period of about 5 years. This outer planet lies well beyond the habitable zone, too cold for liquid water, but its existence hints at a richer planetary system around our nearest stellar neighbour. The search for habitable worlds extends beyond individual systems to statistical questions about the prevalence of potentially life-bearing planets. How common are Earth-sized planets in the habitable zones of Sun-like stars? Kepler data have allowed astronomers to address this question, though the answers remain uncertain due to the challenges of detecting small planets in long-period orbits. Estimates suggest that between 5 and 20% of Sun-like stars host an Earth-sized planet in the habitable zone. With roughly 200 billion stars in the Milky Way, and perhaps 20% of them being Sun-like, this implies billions of potentially habitable, Earth-like worlds in our galaxy alone. Even if only a tiny fraction of these planets actually developed life, the numbers suggest that we may not be alone. The Drake equation, formulated by astronomer Frank Drake in 1961, provides a framework for estimating the number of communicative civilizations in the galaxy. The equation multiplies together factors, including the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction of habitable planets where life arises, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology, and the average lifetime of technological civilizations. When Drake first proposed his equation, most of these factors were unknown. Today, thanks to exoplanet discoveries, we have reasonable estimates for the first three factors. We know that most stars have planets, and we know that Earth-sized planets in habitable zones are common. The remaining factors, dealing with the origin and evolution of life and intelligence, remain deeply uncertain, but the astronomical terms of the equation have been transformed from speculation to measured values. The search for biosignatures represents the next frontier in the quest for habitable worlds. A biosignature is any observable feature that indicates the presence of life, whether past or present. On Earth, the most obvious biosignature is the presence of oxygen in the atmosphere, a gas that would quickly disappear if not continuously replenished by photosynthesis. Other potential biosignatures include methane, nitrous oxide, and various organic molecules that are associated with biological processes. Detecting biosignatures in exoplanet atmospheres is extraordinarily challenging. The signals are faint, the observations difficult, and the interpretation ambiguous. Oxygen can be produced by non-biological processes, such as the photodissociation of water vapour, followed by hydrogen escape. Methane can arise from geological sources as well as biological ones. A convincing detection of life would likely require multiple biosignatures observed together, creating a pattern that is difficult to explain without invoking biology. The James Webb Space Telescope has begun to characterize the atmospheres of potentially habitable exoplanets, searching for the chemical fingerprints that might indicate habitability or even life. Future missions, such as the Habitable Worlds Observatory, aim to directly image Earth-like planets around nearby stars and analyze their atmospheres in detail. The detection of biosignatures, if it comes, would rank among the most profound discoveries in human history. As you relax and let your thoughts drift, imagine the possibilities. Somewhere in the vastness of space there may be a world much like Earth, with blue oceans and green continents, with clouds drifting across a temperate sky. On that world, life may have arisen, evolved, and perhaps even developed intelligence. Beings on that distant planet may gaze up at their night sky and wonder, as we do, whether anyone is out there. The search for habitable worlds is ultimately a search for connection, for the knowledge that we are part of a living universe, that the spark of life has ignited not just here, but elsewhere among the stars. Characterizing exoplanet atmospheres. The discovery of exoplanets was just the beginning. To truly understand these distant worlds, we must go beyond simply detecting their presence and begin characterizing their properties in detail. The atmosphere of a planet holds crucial clues about its composition, climate, and potential habitability. Over the past 2 decades, astronomers have developed techniques to probe exoplanet atmospheres, revealing a diversity of chemical compositions and atmospheric conditions that continues to surprise and delight. Transmission spectroscopy provides the primary window into exoplanet atmospheres. When a planet transits its star, some of the starlight passes through the thin ring of atmosphere at the planet's edge. Different molecules in the atmosphere absorb light at specific wavelengths, leaving characteristic fingerprints in the transmitted spectrum. By comparing the spectrum of the star during transit to its spectrum outside of transit, astronomers can identify the chemical constituents of the planetary atmosphere. The technique requires extraordinarily precise measurements. The atmospheric absorption signal is tiny, typically changing the apparent size of the planet by less than 1% at wavelengths where molecules absorb. Detecting this signal requires observations from space or from the largest ground-based telescopes, using instruments specifically designed for high-precision spectroscopy. Even then, systematic effects from the instrument, the telescope, and the Earth's atmosphere must be carefully modelled and removed. The first detection of an exoplanet atmosphere came in 2001, when astronomers observed sodium in the atmosphere of HD 29458b, a hot Jupiter about 150 light-years away. The detection used the Hubble Space Telescope spectrograph to measure the slight increase in absorption at the wavelength of sodium's characteristic spectral line during transit. This pioneering observation demonstrated that atmospheric characterization was possible and opened a new chapter in exoplanet science. Since then, transmission spectroscopy has revealed a wealth of information about exoplanet atmospheres. Water vapor has been detected in numerous hot Jupiters and smaller planets, confirming that water is common in planetary systems throughout the galaxy. Carbon dioxide, carbon monoxide, and methane have been identified, along with more exotic species like titanium oxide and vanadium oxide in the hottest atmospheres. Clouds and hazes have been inferred from muted spectral features, indicating that many exoplanets' atmospheres are not clear but shrouded in aerosols. The interpretation of transmission spectra is not always straightforward. Clouds and hazes can obscure the deeper atmosphere, flattening spectral features and making it difficult to determine the atmospheric composition. The geometry of the observation means that we sample only the upper atmosphere at the terminator, which may not be representative of conditions elsewhere on the planet. And degeneracies in the models mean that different atmospheric compositions can sometimes produce similar spectra. Emission spectroscopy offers a complementary approach, measuring the light emitted by the planet itself rather than the starlight filtering through its atmosphere. During secondary eclipse, when the planet passes behind the star, the combined light of the star and planet drops as the planet's contribution is blocked. By measuring this drop at different wavelengths, astronomers can determine the spectrum of the planet's dayside emission. Emission spectroscopy is most effective for hot planets that emit significant infrared radiation. Hot Jupiters with dayside temperatures of thousands of degrees are ideal targets. Their emission spectra reveal the temperature structure of the atmosphere, with different wavelengths probing different atmospheric depths. Features in the emission spectrum indicate the presence of absorbing molecules, while the overall shape of the spectrum constrains the temperature profile. The Spitzer Space Telescope, which operated from 2003 to 2020, was a workhorse for emission spectroscopy of exoplanets. Its infrared detectors were well suited to measuring the thermal emission of hot planets, and it observed secondary eclipses and phase curves for dozens of worlds. Spitzer revealed temperature inversions in some hot Jupiter atmospheres, where temperatures increase with altitude in the upper atmosphere, similar to the stratosphere on Earth. Phase curves track the brightness of the star-planet system as the planet orbits, revealing how the planet's apparent brightness changes as different portions of its surface rotate into view. For a tidally locked hot Jupiter, the brightness peaks just before secondary eclipse, when the hot day side is fully visible and reaches a minimum during transit, when we see the cooler night side. The amplitude and shape of the phase curve reveal the day-night temperature contrast and the efficiency of heat redistribution by atmospheric winds. Phase curve observations have revealed that hot Jupiters have diverse atmospheric dynamics. Some show large day-night temperature contrasts, indicating inefficient heat redistribution, while others have more uniform temperatures, suggesting strong winds that carry heat from day to night. The hottest hot Jupiters tend to have larger temperature contrasts, possibly because their atmospheres are too hot for the clouds that might otherwise help distribute heat. High-resolution spectroscopy from ground-based telescopes has emerged as a powerful technique for atmospheric characterization. By resolving individual spectral lines, astronomers can detect the Doppler shift of atmospheric absorption as the planet moves in its orbit. This technique can identify specific molecules with high confidence and even measure atmospheric winds by detecting the slight shifts in line positions caused by moving air. The espresso and HARPS spectrographs have detected iron, magnesium, sodium, and other elements in the atmospheres of ultra-hot Jupiters, worlds so hot that metals vaporize into the atmosphere. These observations have revealed atmospheric escape, with material streaming away from the planet under the intense radiation of the nearby star. They have detected asymmetries between the morning and evening terminators, indicating different chemical compositions on the two sides of the planet. The James Webb Space Telescope, launched in December 2021, represents a transformative advance in atmospheric characterization. Its large mirror and infrared sensitivity allow it to detect fainter signals from smaller, cooler planets than previous instruments could study. TESS has already begun observing exoplanet atmospheres, with results that are reshaping our understanding of these distant worlds. One of JWST's early highlights was the observation of WASP 39b, a hot Saturn about 700 light-years away. The telescope detected water, carbon dioxide, carbon monoxide, sodium, potassium, and sulfur dioxide in the planet's atmosphere. The most complete chemical inventory ever obtained for an exoplanet. The detection of sulfur dioxide was particularly significant, as this molecule is produced by photochemistry, sunlight-driven reactions in the upper atmosphere. Its presence demonstrates that JWST can probe the chemical processes shaping exoplanet atmospheres. JWST has also observed smaller, potentially habitable planets. K2-18ab, a sub-Neptune about 8.5 times Earth's mass orbiting in the habitable zone of a red dwarf, was observed in 2023. The telescope detected carbon dioxide and methane in the planet's atmosphere, along with a possible hint of dimethyl sulfide, a molecule that on Earth is produced primarily by marine organisms. While the detection of dimethyl sulfide remains tentative and could have non-biological explanations, it illustrates the tantalizing possibilities that JWST opens for biosignature searches. The interpretation of K2-18b's atmosphere remains debated. Some researchers suggest that the planet could be a Haitian world, with a hydrogen-rich atmosphere overlying a global ocean. Others argue that the observed spectrum is consistent with a mini-Neptune with no surface at all, just a deep gaseous envelope surrounding a rocky core. Distinguishing between these possibilities will require additional observations and more sophisticated atmospheric models. TRAPPIST-1, B and C, the two innermost planets of the TRAPPIST-1 system, have also been observed by JWST. These observations aim to determine whether the planets have retained atmospheres despite the intense radiation from their nearby star. Initial results suggest that TRAPPIST-11b has little or no atmosphere, its surface exposed directly to space. TRAPPIST-1e may have a thin atmosphere, possibly dominated by carbon dioxide, but the data remain inconclusive. Observations of the potentially habitable planets TRAPPIST-1e, F and G are planned and eagerly anticipated. Atmospheric escape is a crucial process that shapes the evolution of exoplanet atmospheres. Planets close to their stars receive intense radiation that can heat the upper atmosphere and drive material into space. This process, called photoevaporation, can strip away entire atmospheres over billions of years, transforming gas-rich mini-Neptunes into bare rocky cores. The radius valley in the exoplanet population, the deficit of planets between about 1.5 and 2 Earth radii, is thought to result from this atmospheric loss. observations of atmospheric escape have detected extended envelopes of hydrogen, helium, and heavier elements streaming away from close-in planets. These observations use transmission spectroscopy at ultraviolet and infrared wavelengths, where escaping atoms and ions absorb strongly. The escape rates can be substantial, with some planets losing millions of tons of atmosphere per second, though even at these rates, a massive atmosphere can persist for billions of years. The future of atmospheric characterization is bright. JWST will continue to observe exoplanet atmospheres for years to come, building up a statistical sample of atmospheric compositions across different planet types. Ground-based extremely large telescopes, with mirrors 30 meters or more in diameter, will enable high-resolution spectroscopy of fainter targets. And future space missions will push toward the ultimate goal of characterizing the atmospheres of Earth-like planets around nearby Sun-like stars. As you breathe slowly and let your body relax, consider the remarkable journey from detecting a planet's existence to understanding its atmosphere. Each observation adds a piece to the puzzle, revealing the chemistry, climate, and dynamics of worlds we will never visit. The light from distant stars carries information about alien skies, encoded in the wavelengths absorbed and emitted by molecules we know from our own world. Reading this cosmic message requires patience, precision, and ingenuity, but the rewards are glimpses of worlds beyond imagination. The future of exoplanet science and closing reflections. As we near the end of our journey through the story of exoplanets, we turn our gaze forward toward the missions and discoveries that await in the coming years and decades. The pace of progress shows no sign of slowing. New telescopes, new techniques, and new ideas continue to push the boundaries of what we can discover and understand. The future of exoplanet science promises revelations that may transform our understanding of our place in the universe. The European Space Agency's Plato mission, scheduled for launch in 2026, will search for Earth-like planets around Sun-like stars. Plato, which stands for planetary transits and oscillations of stars, will carry 26 cameras that will monitor thousands of bright nearby stars for transiting planets. Unlike Kepler, which focused on a single field of faint stars, Plato will observe brighter targets that are better suited for follow-up characterization. Plato's primary goal is to find and characterize Earth-sized planets in the habitable zones of Sun-like stars. These are the most challenging targets to detect, requiring long observational baselines to capture the year-long orbital periods and high photometric precision to detect the shallow transits. Plato's design is optimized for this task, with overlapping camera fields that provide continuous coverage and redundancy against instrument failures. The mission will also characterize the host stars through astroseismology, the study of stellar oscillations. Stars vibrate in complex patterns with sound waves bouncing through their interiors. By measuring these oscillations, astronomers can determine the star's mass, radius, and age with high precision. Knowing the star's properties precisely is essential for determining the properties of any orbiting planets. The aerial mission, also from the European Space Agency and scheduled for launch in 2029, will focus on atmospheric characterization. Aerial, which stands for Atmospheric Remote Sensing Infrared Exoplanet Large Survey, will observe the atmospheres of approximately 1,000 exoplanets, building up a statistical sample of atmospheric compositions across different planet types. Aerial will use transmission and emission spectroscopy to measure the chemical compositions, temperatures, and cloud properties of exoplanet atmospheres. By observing a large number of planets, the mission will reveal how atmospheric properties depend on planet size, orbital distance, and host star type. This statistical approach will complement the detailed studies of individual planets conducted by JWST, providing context for interpreting those observations. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will advance exoplanet science through multiple approaches. Its wide-field infrared camera will conduct a microlensing survey toward the galactic center, detecting thousands of planets at orbital distances where other methods struggle. This survey will reveal the population of planets in the outer regions of their systems, including free-floating planets unbound to any star. Roman will also carry a coronagraph technology demonstrator, an instrument designed to block the light of nearby stars and reveal orbiting planets. While not expected to image Earth-like planets directly, the coronagraph will advance the technology needed for future missions and may detect giant planets around nearby stars. The lessons learned from Roman's coronagraph will inform the design of more ambitious instruments. The Habitable Worlds Observatory represents the long-term vision for exoplanet science. This concept, recommended by the Astro 2020 Decadal Survey, would be a large space telescope specifically designed to directly image Earth-like planets in the habitable zones of nearby Sun-like stars. With a mirror 6 meters or more in diameter and an advanced coronagraph or starshade, the Habitable Worlds Observatory could photograph dozens of potentially habitable worlds and analyze their atmospheres for signs of life. The technical challenges are formidable. Imaging an Earth-like planet requires suppressing the light of the parent star by a factor of 10 billion, revealing a planet that appears as close to the star as a few hundredths of an arc-second. The telescope must be extraordinarily stable, with the vibrations controlled to picometer precision, and the observations must be long enough to accumulate sufficient photons from the faint planetary light. Despite these challenges, the technology is advancing rapidly. Laboratory demonstrations have achieved the required contrast levels in controlled environments. Space-based starshade concepts have been refined to the point where they could be deployed in the coming decades. The Habitable Worlds Observatory remains a goal for the 2030s or 2040s, but the path forward is becoming clearer. Ground-based extremely large telescopes will also contribute to the future of exoplanet science. The European Southern Observatory's extremely large telescope, with a 39-metre primary mirror, is under construction in Chile and expected to see first light in the late 2020s. The Giant Magellan Telescope and the 30-metre telescope are also in development. These massive instruments will enable high-resolution spectroscopy of exoplanet atmospheres, potentially detecting biosignatures in the atmospheres of nearby rocky planets. The search for technosignatures represents another frontier. While biosignatures indicate the presence of life, technosignatures indicate the presence of technology, signs of intelligent civilizations that have modified their environments or communicate across space. Radio telescopes have searched for artificial signals for decades without success, but new instruments and approaches are expanding the search. The Breakthrough Listen initiative, funded by entrepreneur Yuri Milner, is conducting the most comprehensive search for technosignatures ever undertaken. Using some of the world's largest radio telescopes, the project is surveying nearby stars, the galactic plane, and other galaxies for signs of artificial transmissions. While no confirmed detections have been made, the search continues, driven by the profound implications that a positive result would have. Optical technosignatures are also being sought. A sufficiently advanced civilization might use powerful lasers for communication or propulsion, producing brief flashes of light that could be detected across interstellar distances. Surveys are searching for such flashes. though distinguishing artificial signals from natural phenomena remains challenging. The detection of life beyond Earth, whether microbial or intelligent, would rank among the most significant discoveries in human history. It would answer a question that has haunted humanity since we first looked up at the stars and wondered whether we were alone. It would transform our understanding of biology, showing that life is not a unique accident, but a natural outcome of cosmic chemistry. And it would reshape our sense of our place in the universe, connecting us to a community of living worlds scattered throughout the galaxy. Even if we never detect life elsewhere, the search itself has value. The exoplanets we have discovered reveal the diversity of planetary systems and the processes that shape them. They show us that our solar system is just one possibility among countless variations, that nature is more creative than we imagined. They inspire wonder and curiosity, driving us to develop new technologies and ask new questions. As you settle into deeper relaxation, let your mind wander through the possibilities that the future holds. Imagine the moment when a spectrum from a distant planet reveals the unmistakable signature of life, when we know for certain that we are not alone. Imagine the headlines, the celebrations, the profound shift in how humanity sees itself. Or imagine the continued search, the steady accumulation of knowledge, the gradual mapping of a universe rich with worlds, even if life proves rare. The story of exoplanets is ultimately a story about us, about human curiosity and ingenuity, about our desire to understand our place in the cosmos. From ancient philosophers who imagined infinite worlds to modern astronomers who detect them with precision instruments, the quest has spanned millennia and engaged countless minds. Each discovery builds on those that came before. Each question answered opens new questions to explore. We live in a remarkable time when questions that seemed unanswerable are yielding to observation and analysis. The first exoplanets were discovered within living memory, and already we know of thousands of worlds orbiting other stars. We have begun to characterize their atmospheres, to map their temperatures, to understand their compositions. We have found planets in the habitable zones of their stars, worlds where conditions might be right for life. The universe has proven generous with its wonders. Every new observation reveals something unexpected, some twist that challenges our models and expands our understanding. Hot Jupiters that should not exist, super-Earths with no analogue in our solar system, resonant chains of planets locked in gravitational harmony, rogue worlds drifting through the darkness between stars. The cosmic zoo grows ever more diverse, ever more fascinating. And yet, for all we have learned, the greatest discoveries may still lie ahead. The first detection of biosignatures in an exoplanet atmosphere. The first image of an Earth-like world around a sun-like star. The first confirmation that life exists beyond our pale blue dot. These milestones await future generations of scientists, future missions, future technologies. But the foundation has been laid, the path has been cleared, and the journey continues. As you drift towards sleep, carry with you the wonder of distant worlds. Let the knowledge that planets orbit countless stars bring a sense of connection to the cosmos, a feeling of being part of something vast and beautiful. The universe is not empty, but full of worlds, each with its own story, its own possibilities. We are explorers at the beginning of a great adventure, mapping the shores of an ocean we have only begun to sail. Thank you for joining me on this journey through the entire story of exoplanets, from ancient dreams to modern discoveries, from the first tentative detections to the thousands of worlds now known. We have traced a path of wonder and discovery. The story continues, written in the light of distant stars, waiting to be read by those with the curiosity to look. If you enjoyed this exploration of the cosmos, please consider liking this video and subscribing to the channel. Your support helps create more content that brings the wonders of the universe to life. Share this video with friends who might enjoy a peaceful journey through the stars, and leave a comment with your thoughts on exoplanets or suggestions for future topics. Until next time, rest well, dream of distant worlds, and remember that the universe is vast, beautiful, and full of possibilities waiting to be discovered. Good night and clear skies.